Mark said, I'm not going to talk about why we should be concerned about groundwater. The question is, should we be concerned about groundwater infiltration in the groundwater system? Hopefully we'll get at some of that during this talk. So I was actually supposed to give this talk back in February at the watersheds meeting, and the weather got in the way of that, so I was asked by a couple of folks to go ahead and give this talk again. Unfortunate thing for you is that was a 20-minute talk. This is an hour talk. So I'm going to have to put up. I'm going to spend a fair amount of time talking about chloride in the environment before I get to the actual infiltration stuff. I think it's important to understand some of those concepts before I actually get to what's 10-12 slides, which will focus specifically on the stormwater infiltration aspect of it. So we'll talk a little bit about the problem with chloride and infiltration, give an overview of that. I gave a presentation back in 2015 that I'll revisit real quickly. And then we'll talk about chloride and stormwater runoff, because that's the source of chloride in urban areas. And again, I'm focusing on urban areas because that's the world of stormwater that we live in. And then the last few bullets here are dealing with the actual infiltration stuff. So obviously chloride's in the news a lot. We see headlines such as this here. And our receiving waters are showing elevated concentrations of it. Right now we've got about 26 lakes, and we have 26 lakes, 24 streams listed as impaired. These are aquatic life impairments, which the standard is 230 parts per million for that. Most of that, of course, is in the metro area or other. This is the Twin Cities metro area, but also other metro areas. You can extrapolate the similar data. So most of the impairments are occurring in the Twin Cities metro area, and about 30% of shallow wells are exceeding the SM secondary maximum contaminant level, which is 250 parts per million in groundwater. And of course, if you look at a map, this shows the urban metro area, and you can see the red and the orange. Those are the places where we have the high concentration. The red are impairments. The orange are places where we have water bodies that are considered to be at risk of maybe potentially becoming impaired at some point. And of course, the focus is in the central part of the metro area, which is what you would expect: greater road density, probably higher applications of road salt. You see similar patterns in groundwater. This is from MPCA data that Sharon works with. The data is biased a little bit towards urban areas because that's what they mostly sample, but there's enough rural data in here, data from rural areas in here, to show that indeed the concerns are going to be in the metro area, particularly in the core metro area. So the red again is bad, and blue is good. We have upward trends in 46 of 69 lakes in the metro area. This shows all the lakes that have upward trends in chloride concentrations, and the circles show the percent increase annually in increase. So we see where the darkest red areas are. We're looking at 5% increases annually in chloride concentration. So that's pretty significant numbers for some of these water bodies. We have upward trends in about 11 of 36 wells in shallow sand and gravel aquifers, and again, these are going to be in the urban areas, the red areas. So chloride trending up in our water bodies. Is chloride a problem? I think it's a fair question to ask. And I gave a talk at the U about 3 weeks ago, and that was more big picture talk about chloride in all our receiving waters. And we have to take a look at, well, what are going to be the impacts of this chloride? And I tried to look for some recent literature on this data, on the effects of chloride. And this recent study by Heinz and others show that there are negative impacts on zooplankton and positive responses by phytoplankton to chloride. So we're seeing ecosystem disruptions in, particularly in lakes, but in receiving waters. In a Maryland study, they noticed that the benthic indicator of biological integrity began to decline at about 190. By the time we got to that 230 part per million threshold, that in fact these systems were becoming fairly degraded. Lakes, you've all heard, I'm sure, about chemostratification. Saltier water is going to move to the bottom of the lake. And what that's going to do is it's going to interrupt the nutrient cycling. And so That's being studied now by several University of Minnesota researchers, looking at what the potential impacts of that are. If the lake doesn't turn over, that's a problem. If it only turns over once a year, that can be a problem because you can export phosphorus, for example. But this is not an area that's been extensively studied. It's being looked at in greater detail now. We know it happens. We're not quite sure about what the ecological impacts of that are going to be. And there's salty taste in drinking water, and that's the endpoint that we have for groundwater systems right now. There are other negative impacts. I'm not going to talk about them of having chloride in the environment. We're all aware that it leads to corrosion. It has damages vegetation. It can increase the mobility of certain metals. I just wanted to throw that out there. That's not going to be the focus of this talk, obviously. So kind of a 101 on stormwater infiltration. I'm sure you're all aware of this, but it doesn't hurt just to go over it real quickly. Stormwater infiltration, as we define it in our program, is the intentional infiltration of stormwater runoff. So what we're doing is stormwater runoff is flowing from the right to the left at the top of this, and it's captured by this infiltration practice. That practice is designed to hold a certain amount of water. Generally, it's going to be 1 inch off of all the impervious surface that's draining to that particular practice. For those of you who are familiar with MIDS, that's 1.1 inch. There may be other standards out there, but so these things are taking a lot of water. They hold that water for 48 hours or less, and they infiltrate it into where it eventually reaches the groundwater system below. You compare that to what we call an underdrain system, which also captures this water, but here the water gets filtered through a media, and then it gets returned through this underdrain back to the storm sewer system. So in these systems, maybe only 10, possibly as much as 20% of the water might get below that underdrain and infiltrate. The infiltration systems on the left infiltrate 100% of the water that they capture. And some typical practices that we've seen are rain gardens. You're all familiar with that. We call them bioinfiltration systems. Tree trenches and tree boxes. The green line in St. Paul, for example, underneath it is a massive infiltration system. Infiltration basins and trenches. These can be above ground or below ground. The below ground ones can actually take significant quantities of water. They can drain areas 10, 20 acres in size, for example. Permeable pavements, asphalt, concrete, and pavers. And some swales. If we build swales with these check dams in, we can capture the water behind it, hold that water, and allow it to soak in. So some swales are designed for infiltration. Stormwater infiltration is a preferred practice. We're not doing this for no reason at all. We generally like to have reasons for doing things. It benefits surface water. All the water that gets captured and infiltrated is water that's not going to a surface water. And stormwater pollution, or stormwater is a source of pollution. It has high concentrations of phosphorus. It has high concentrations of chloride. It has metals in it. Sometimes it has organics in it. And it's got bacteria and pathogens in it too. It more closely mimics the natural hydrology compared to the old pipe and pond system where we capture water in these big pond systems and then treat it there a little bit, and then it would go to a receiving water. These infiltration systems are designed to keep the water close to where the rain falls. They can use space efficiently. The green line, for example, where would you be able to put a massive surface infiltration system? So you can put it underground. So that's why we can infiltrate that water along the green line. They can provide ecosystem services. This rain garden here is using perennial vegetation, which can be great habitat for pollinators and so forth. And they effectively treat pollutants, except for chloride. So these systems focus recharge. So if you build an infiltration system that captures 1 inch of rainfall off of 1 acre of impervious surface, depending on the underlying soil and how you design that system, you're going to infiltrate 35 to 75 feet of water in that system. You compare that to a ball field where it rains, and during the course of a year, you might get 6 to 12 inches of infiltration through that system. Here we're infiltrating 50 feet of water, plus or minus. So we're really focusing a lot of water in one area. And that's the question, is that going to be a problem or not? All right, who's old enough and brave enough to admit that they actually watched this show when they were young? So I'm going to go back 2.5 years, and I gave a talk on effects of stormwater infiltration on groundwater. So this was all pollutants. We were looking at all pollutants back then. But I'm going to look at the chloride stuff and I went back and looked at it. And I copied the notes that I had from that into this presentation. So at the time I said chloride cannot be treated with stormwater BMPs. Prevention is the only effective management tool, but we need to better understand dynamics of chloride in our urban systems. The risks to groundwater are high based on its mobility. Chloride is a mobile contaminant. It's conservative. It's not attenuated in soils, for example, to any high degree. Some preliminary data suggests a seasonal lag in peak concentration in groundwater. Remember now, this is 2.5 years ago. And concentrations in groundwater are not likely to reach 250 parts per million, but there may be impacts to lakes and streams. So, was I telling the truth or not? So, shortly after that presentation, I had the idea, well, I've lived in both worlds. I had Sharon's job before she came in. Mindy Erickson worked at it for a little bit, but Sharon came in. So I lived in the groundwater world for about 15 years, and now I've been living in the stormwater world for about 12 or 13 years. And so I would hear, when I talked to groundwater people, I'd hear things like, those stormwater people are contaminating all our groundwater. When I talked to stormwater people, they were just infiltrating, it's not going to be a problem. And I thought, well, maybe we should get the two groups together and start talking to each other a little bit. And so we started doing that, and chloride kept coming up. Well, what about chloride? What about chloride? And so we formed a group through the Minnesota Groundwater Association, and they accepted our proposal to develop a white paper called The Impacts of Stormwater Infiltration on Chloride in Groundwater. And Sharon's part of that group. And the group is still working on the white paper, but I think we're far enough along to present some data, and that was the focus behind me wanting to give that talk in February that I'm now giving today. So let's start by looking at where's the chloride coming from. So some work that Alicia Overbo is doing at the University of Minnesota with others is showing clearly that chloride in urban systems, the primary source by far and away is road salt. And you can do all kinds of chloride-bromide ratios analysis and so forth to show that. And you can see that chloride road salt use has gone up dramatically since we stopped sanding back in the 1990s. So we're putting a lot of chloride into our systems, and most of it is from road salt. So I'll try to walk you through these slides a little bit. So this is from Granado and Smith. It's a 20-year-old study, but it does a good job of showing concentrations of chloride in runoff. So this is the chloride that's in the stormwater runoff that's running off this parking lot or the street or whatever. And you can see there's a log scale on the y-axis. And you can see that in the wintertime, during the de-icing season, that we're looking at typical concentrations of about 1,000 parts per million, and sometimes we're up over 10,000 parts per million. After the de-icing season ends, we drop quickly back into a range of about 20 to 30 parts per million. Another thing that's interesting, if you look at chloride and runoff from areas that receive high de-icer application, shown in the blue, to areas that don't receive de-icer application or very little, shown in the orange, after the de-icing season, we still see elevated concentrations of chloride in those areas where de-icer is applied in the wintertime. And that's because there's a lot of residual chloride left in the system. Chloride gets hung up. You can still walk the streets, sidewalks now. You can still see some salt out there. There's some chloride in the bed that gets trapped in the vegetation and so forth. So it's not completely conservative in the sense that it's always going to wash away with all the water when the snow melts. So we still see elevated concentrations in runoff even as late as August. But we're down around less than 100 parts per million. All right, so the university, Bill Erb has been doing some work with some other researchers. If you look at this bar chart, the chloride is mass. This is a mass of chloride in runoff. It's shown in the dark boxes. And you can see that almost all of the mass of chloride in runoff occurs during the de-icing season. The lighter hashed blue boxes show the volume of water in stormwater runoff. And so we're seeing 90% or more of the chloride in our runoff happening with about 15% of the stormwater volume that occurs during the course of the year. So that's what we're really interested in. We're interested in that runoff during that part of the time of the year when we get those little bit of snow melts in the winter time, and then we get that first snow melt in the spring. Switching to groundwater, chloride is elevated in shallow groundwater. If you look at urban areas shown in box C to the right, you can see, and again we've got a log scale, we can see that the concentrations are significantly greater than they are in forested and agricultural areas shown in the other two boxes. And this is a USGS study done about 10 years ago. And these are median concentrations. Again, in groundwater you can see the medians maybe in the 50 part per million range. This is work that the MPCA ambient monitoring program is put together. The medians are shown in blue and the maximum concentrations in red. And you can see that commercial industrial areas, the far left, we're looking at the highest median concentrations, about 82 parts per million in shallow. These are shallow groundwater, shallow sand and gravel aquifers. In sewer residential areas, we're still elevated well above agricultural and undeveloped areas, but we're less than commercial industrial areas, and about 45 parts per million. You can also see that some of the concentrations that we're seeing in shallow groundwater are quite high, 790 parts per million. I think, Sharon, you've seen some over 1,000, haven't you?
Yes, we had a well that we'd sampled several years ago right near a gas station where it was almost 10,000.
So yeah, we can get some pretty high numbers in shallow groundwater in urban systems. The factors affecting chloride in shallow aquifers, this is again from the USGS study done 10 years ago. They did several regressions of different factors looking at what factors are going to affect the chloride concentration in groundwater. They only found one significant relationship, and that was to major road density. And their test value was 0.05. They looked at a whole bunch of other factors. I'm not going to go through all of them in detail, but the point is that major road density was the one indicator that stood out as an indication of what you're going to find in groundwater. Now, I believe that our ambient program is looking at some additional data to try to ferret out some of this type of information of land use and road density and things like that. And, but it takes time, unfortunately, to come up with results. One thing that I did find interesting, if you look at the last bullet, season is not a significant predictor of chloride concentration in groundwater. You might think in shallow groundwater systems, right after recharge happens in snowmelt, you're going to see higher chloride concentrations. That's not the case. Not only the USGS study, but the ambient work that I was doing back in the late 90s shows that, in fact, the concentrations through all the seasons in shallow groundwater are the same in these urban areas. And I'll talk a little bit about why that is later when I get to the infiltration.
I have a quick question.
Yes?
What is considered the definition of major road density?
I'd have to go back in and to the USGS study, but Snelling Avenue, University Avenue would be major roads.
Okay.
And it's interesting that if you look at major highway density, which would be like 94 or something like that, that was not a significant.
So it's independent of just straight impervious surface, or
it is
associated?
It is, yeah. So, and the part of the problem is here is we're trying to. We can't get good data for how much salt is being applied by cities over certain stretches of road. And we can get ideas about how much they're applying across their city, maybe even on a neighborhood basis, but on specific road miles and so forth, that data is very hard to come by. And that's why the USGS and others have looked at these types of factors. So you think about major roads are the ones that are probably getting the de-icer the most. Okay, so we're getting higher concentrations of chloride in our groundwater. What are the consequences of that? Shallow sand and gravel aquifers are impacted. We know that, and is that a problem? And I think it's a fair question, but it has to be answered from a number of ways. We need to look at, and I'm going to look at three things. Streams, effects on streams, effects on lakes, and effects on deeper groundwater systems. A person could make an argument that, well, if you have 1,000 parts per million, right below me here, there are no receptors around, so it's not going to be an issue. Well, I think we need to think a little bit bigger picture than that. So let's start by looking at urban streams. Urban streams that get significant base flow are potentially going to be at risk. So Baseflow 101, for those I'm sure you're all familiar with, just in case you're not. So baseflow is that portion of a stream flow that's contributed by subsurface flow, that is groundwater. So when it rains, if you look at a stormwater hydrograph here, when it rains, after significant rain, the stream flow is going to jump way up. Most of that is coming from direct runoff over the land surface. But there's this component below that's going into the stream that's coming from the groundwater that's moving into that stream. And the recession part of this curve, and now that overland runoff has gotten into the stream, it's gotten washed down the stream, but we still have this base flow component. So this is a continual contribution to the stream from the groundwater system. If we look at a creek like Miller Creek in Duluth, which has very little base flow, and you look at the chloride concentrations on the y-axis, you can see we get some very high numbers, 1,400 parts per million in the creek during the de-icing season. And that's because it's reflecting runoff. It's almost pure runoff in the creek. In fact, if you plot the snowmelt data on shown in the purple on top of the data in the creek, they match up, which basically is saying that the water in the creek is stormwater runoff. So this system is really vulnerable in the wintertime and the early spring when we're getting that first flush of chloride. It's not so vulnerable later in the year because by then, if it's getting runoff from streets, it's getting maybe 25, 50 parts per million chloride. You compare that to Bassett Creek in Minneapolis, which is a base flow fed creek, you see that the peak in the wintertime is down to a little over 300. So it's not, we don't get that real sharp peak in the wintertime like we did in Miller Creek. Groundwater is damping out that high peak. But what we're getting is we're getting elevated concentrations throughout the year. Because groundwater maybe has 100 parts per million chloride in it. So that's diluting that surface runoff in the early spring, or later in the summer when you're getting mostly groundwater in the creek. We're keeping that higher concentration in the creek. So obviously, if we have a groundwater system that is highly impacted by chloride, any base flow fed streams in the area are going to be potentially at risk. Conversely, if our groundwater is clean, those streams have a greater buffering capacity for meeting required currents. What about lakes? Well, lakes are trickier. This is a little bit misleading, but most of our lakes, again, in the metro, are connected to the groundwater system. This shows a groundwater discharge lake, but a lot of times groundwater just flows through these systems too instead. But if you look at Worth Lake, which does receive a groundwater contribution, you can see that if you look at the winter concentrations and the summer concentrations, they plot almost on top of each other. So what this is saying is that for this particular lake, that the groundwater contribution is very important. Because otherwise we would see higher concentrations in the winter when we're getting that winter flush. It does happen on occasion. In 2011, we got higher concentrations. I'm not sure exactly what happened in that particular year. So this would be a lake that is potentially at risk. Lakes are tricky though. Any hydrologists, limnologists in the room? The residence time in most Minnesota lakes is going to be 3 years or less. Now, I say that because as a hydrologist, they're going to cringe and say, you know, you can't throw a number like that out there. It could vary from months to decades. But on average, you know, we're looking at about 1 to 3 year residence time. So the water that's coming in isn't going to get all flushed through right away. Some of it's going to stay behind. So it's a little bit trickier with lakes. And another problem with lakes, if you look at this plot here, if you measure the concentration at the top, near the top of the lake and measure the concentration at the bottom of the lake, concentration at the bottom of the lake is always going to be higher than at the top. And that's because we have that chemostratification, the denser layer down there. So lakes are tricky, and I'm preparing, I mean, this is a research project, and preparing for this talk, I wasn't going to be getting into that level of detail, but lakes are certainly at risk. but individual lakes are difficult to study. This morning, it's good to know that at my age I still have interest in doing things. So this morning I thought, well, you know, Christopher Parsons sent me this great data set showing me median lake concentrations in Minnesota. And I thought, well, what if I plot those on a geologic map showing groundwater, or showing glacial deposits? So the brown hashed areas are places where we have sandy soils. And the places where we have white soils are going to be tighter soils, where we're not going to expect much recharge. So these areas here are going to be vulnerable to potential contamination, water moving through, because these are rapid response systems compared to the other ones. So I threw this data up and I ran some numbers on it, and I'll throw a question out there. Where would you expect the concentrations of chloride to be higher? In the areas that are hashed or the areas in white? Anybody want to take a shot at it? Nobody wants to fall into this trap. The concentrations in the areas in white are about twice as high as in the areas in hashed. And so I just put this up this morning. I'm trying to think about that and thinking, well, probably, possibly, it's a hypothesis, a great research project for anybody who wants to go back to school. Possibly because on an area basis, we got more clean water moving in those brown areas. So we obviously have some lakes that are highly impacted in this area. But in general, on a big area basis, and this is in the core of the metro area, on an area basis, we generally have cleaner water moving into the system, maybe. What about deeper drinking water aquifers? So we got chloride in our shallow system again, I showed that. Most of you are aware that in the metro area here, this is not applicable statewide, but in the metro area here, we've got these alternating Paleozoic deposits. Some of them are aquifers, like the Jordan and Prairie du Chien. Some of them are aquitards, like the Decorah Shale. And so if you plot a map up, and so this is the red box shows the core metro area here, where we expect to see those chloride, potential chloride issues. The areas in dark blue in the lower 1/3 of this diagram are areas where the Prairie du Chien, which is our primary drinking water aquifer, is at risk. The areas in the northern 2/3 have some protection. So it would be in those areas in the southern 1/3 where I might expect to see some potential impacts from chloride loading into the shallow groundwater system. Unfortunately, we don't currently have enough data to look at these trends. And I know Sharon's working on that with her program. It's difficult to get these deeper wells. They're expensive. It's hard to find access to them. But they're working on trying to get this information. And of course, the deeper system is going to take a longer time to respond. So we
we are starting to see some increases in the deeper wells in the Prairie du Chien in Washington County. We've got a lot of wells there. And I'm seeing those in the domestic wells that we've been able to have access to sample on an annual basis. It's going up.
Okay, would that be in the southern 1/3 primarily, Washington County?
Not necessarily, even the central to southern part.
Okay, because that would be out in this area here. I think.
So could you restate that again, at least for me? You're saying that there's potential harm or there's danger for these deeper aquifers, mostly because they're slower to recharge?
I see in the blue area, it's just naturally susceptible to contamination because that rock that forms the aquifer is right close to the land surface, or it's covered by just really sandy soils that allow the recharge water to just percolate down into it fairly quickly compared to if you get over in the green part of that map.
So yeah, these are areas, so we know the shallow system's got chloride impacts. And those dark blue areas are areas where it could just keep moving down. It's not going to hit a confining unit. If it hits a confining unit, it's more likely then to be discharged to the Mississippi or something. So we're going to have to wait on that. And I was a little reluctant to put this slide up, but I thought I'd go ahead and do it anyways. Chicago's aquifer system is different than ours. They rely on unconfined sand and gravel units for their drinking water. So it's not the same type of system we've got here. But I put it up there anyways because if you look, the point here is that if you look at the 6 aquifer systems that are being shown, every one of them shows an upward trend in chloride concentration in groundwater. So these are systems that are vulnerable to potential contamination. Maybe it equates with what I was just talking about a Prairie du Chien system here in the Twin Cities. These are much more rapid response systems because they are closer to the land surface and unprotected. All right, so what happens if we start infiltrating a lot of stormwater? I talked about stormwater as a preferred practice. It's been around for a long time, but we've really started to see a push on it in the last 10 years. And we've got infiltration, volume, we call them volume retention requirements, but that almost always translates into infiltration. So we've got Capital Region Watershed District, where we're sitting right now, very, very assertive, I'll use the word assertive, at infiltrating water. They want to infiltrate it. And as I mentioned before, it's a preferred practice. So there are these potential impacts. I've talked to them. You could impact the lake or stream. You could impact wells or deeper aquifer systems too. Well, we really don't care, right? Because these things are going to freeze up in the winter and the water's not going to infiltrate through them, right? Properly designed functioning infiltration practices perform nearly as well in winter as in the frost-free seasons. And you think about that. These systems are designed to move water through them. So the pore space is filled with air until liquid water moves in them, and that liquid water moves through them quickly. That's what they're designed for. If they freeze up in the winter, it's probably not functioning properly. You think about permeable pavement that you walk on in the wintertime. You don't have to apply salt to it because you can take that liquid water and move it through. The water just doesn't sit there long enough to freeze. So I'm going to walk you through what I thought was a real interesting study that was done at Villanova back in 2009 to try to get an understanding of what is happening to chloride when it goes into an infiltration system. So in this study, they had a rain garden. It was an bioinfiltration system. And they instrumented it with lysimeters at 3 depths, right below the rain garden, at 4 feet below, and at 8 feet below the rain garden. Then they had a shallow well that was about 20 feet directly down gradient of the rain garden. And then they had another well that was 35 feet down gradient of the rain garden. So the groundwater is flowing from left to right in this image. So during the de-icer season, this is water coming in, this is the chloride concentration in the runoff coming into the rain garden. And you can see concentrations of up to 10,000 parts per million coming into this rain garden. After the de-icer season, dropping off back into the 10 to 50 range. Same data I showed basically earlier, so no surprises there. The lysimeter concentrations there was a lag time and there was a much lower concentration in the lysimeters. Concentrations of several hundred parts per million, but not thousands of parts per million. Plus the peaks came later than the peak in the runoff, and the peak persisted later in the runoff. So chloride's moving through the system, but it's not moving through the system as fast as the water. If you look at the monitoring well, you see the peak even more delayed. This is directly down gradient. Now the peak is out into April, well past the de-icing season in this particular area of study. And the down gradient monitoring well was not impacted at all. So chloride is being attenuated, and it's not being held, it's being attenuated, meaning it's being slowed down in this system. And it's taking a while for it to get through. We can use that actually to our advantage in management systems.
But it's a conservative ion, so where's it going? Is it just stuck between the 2 wells, or is it going deeper, or? Most of it is getting into the groundwater system. It's just getting there slower. So it's being held in the pore spaces, dead pore spaces. There is some interaction with the soil
to delays moving through. The actual mechanisms of what's slowing it down have not been studied to any great
But
extent.
if there's a concentration, say, if you're looking at your second or your third monitoring well, number 3, and you're not seeing any change there, but you're obviously seeing changes in concentration from, surface water on down, are you saying it's being bound and held? Or, the concentration is still there, I would think. It's a conservative ion.
Yeah.
Well, I was just noticing that, it's like a 20-foot unsaturated zone, and it may not, the movement of water, infiltrating water through unsaturated soils is much different than through saturated soils, and it's a whole different science. So it doesn't have to be attenuated, it just may not be able to flow
Okay.
consistently because it's not fully saturated.
Well, there's a difference here between flux and concentration, too. I don't think Mike is saying anything here about flux. He's saying concentration. It might be that there's signal dampening.
Yeah, and like I
And
said,
that the total concentration, the total amount may still is conserved, but it's dampened in terms of concentration signal.
right, and this is a 1-year study. The exact mechanisms of what's causing that dampening are not known. John Niebuhr did some similar work from the University of Minnesota, and he speculated that there's some entrapment in pore water that's happening during the season. And then eventually that water does get flushed out.
Okay.
You must move the next pulse through, but you don't move it all through.
Because year after year, if you keep getting these doses of chloride, it continues to pulse through, I would assume.
It should.
On a mass
Now,
basis.
there's also been studies that show that chloride in soil can undergo chlorination reactions with organic matter, so in fact it can be bound. But that's always been, those studies, the only ones that I've seen of that are in forested soils where you have low chloride concentration. So we don't know if that would be an important factor in this or not. So that would be a good area for research too. That's why I hesitated to say that we don't know that it's not bound. We don't think most of it's not bound, but some of it might be getting involved in those reactions too. And again, it's only a 1-year study, so it's really, we have to be careful to say that this well down gradient is not impacted. If we looked at 10 years of data, maybe in fact there would be a slight upward trend in it. So one of the goals of this white paper group is to try to get a handle on what kind of chloride loads we would be seeing in groundwater if we were to widely implement infiltration practices. Unfortunately, urban areas are very complex. It's not just a simple matter of a couple of sources of infiltration. We've got many sources of water that can get into our groundwater system, including leaky pipes coming in, leaky wastewater pipes going out, leaky stormwater pipes going out, surface water interactions. As you all know, our impervious surfaces are not fully impervious, especially this time of the year. And so, believe it or not, there is, in some areas, as much as 10 to 20% of the water that is on impervious surfaces actually infiltrates through those impervious surfaces because of cracks in the road. We've, of course, got natural pervious areas. We've got, and then we've got stormwater practices. We've got infiltration practices. Those are the ones that I'm talking about. We've got these under-drain systems. They always have a little bit of leakage below them. And we've got the old constructed ponds, which were designed for water retention, but of course, nothing is impermeable and water does seep through the bottom of those systems too, although very slowly. In fact, some of the highest concentration plumes that I've seen in the literature are below these old stormwater ponds. And so when you throw an equation together, you got to look at all of these. And there's we didn't come across any one study that looked at chloride loading in urban areas. So what we had to do is we had to go and look at all these different studies and look at the recharge from these different components. And there are studies of that. We've seen studies of leakage from these pipes and so forth. And then look at the concentrations of chloride that's in the water from those systems. And we have a fairly good handle on that, we think. So it's a question of taking that those leakage rates or recharge rates times the concentration, and getting estimates for each of these parameters. So the next slide is a draft, and I need to put that out there because the group is still looking at this. But let's look at a green space area. Maybe has 20, 30% impervious surface, a low chloride concentration, about 25 parts per million. If we infiltrate the water in that area, so we capture the water coming off the impervious surface and we infiltrate it, we're going to contribute about 11% of the annual chloride load going into groundwater. But equally important is that that concentration is very low. So it's 25 parts per million. So I'm kind of maybe getting ahead of myself here, but this might be a scenario where we would really want to promote infiltration because we're moving fairly clean water into the system. If we go to a residential area, which maybe has 30 to 50% impervious, depending on how the rooftop runoff is handled, we're looking now maybe at about 17%. And these are plus or minus. I mean, this could be 10 to 25%, but this is kind of a ballpark number. 17.5% of the chloride load coming in. And now we're at 50 parts per million, which is still pretty low concentration. Bump it up a notch. Now we're in a commercial area where we've got maybe 50% or more impervious surface, and we want to infiltrate that water, which now has maybe 100 parts per million chloride in it because there is some de-icer being applied in this area. Now we're up to close to 25% of the annual load. Now we got 100 parts per million chloride moving into our shallow groundwater system. Now is that going to be a concern or not? That's a good, fair question. That gets back to that question of, well, what happens to the chloride when it's in the groundwater? Is there a delay mechanism in groundwater? Does it flush through quickly? And those are questions we don't have real good answers to. If we go to the midway, where we've maybe got 90% impervious and maybe a chloride concentration over the course of the year of about 500 parts per million. Now most of this is going to happen in the wintertime, so this is an annual average. So in the wintertime, we may be seeing concentrations of a couple thousand parts per million, but in the summer, much less. So this is an annual average chloride concentration. We're now accounting for about 60% of the annual chloride load in this system. So a couple conclusions. Infiltration in areas where de-icers are not extensively used is protective of surface waters and probably also groundwater. I say probably because we don't have the data yet to verify that. But if you're moving 25 to 50 parts per million chloride water into shallow groundwater, it's probably not going to be a long-term problem. You're going to elevate chloride concentrations, but it's probably not going to be a problem. This is a long one. I'll try to walk you through it. Urban streams that have a baseflow component and that are impaired, infiltration may diminish winter concentration, so you're going to bring that winter peak down in these streams, but you may have higher concentrations throughout the rest of the year. So the question here is, this can be a good thing if you have a creek that's sensitive to those winter peaks, provided your groundwater concentration is below the aquatic life standard of 230. So if you had a groundwater concentration of 150, it's high, but you're moving it into a stream and you're dampening out that winter peak a little bit. So the key here is, well, what's the concentration in groundwater going into that receiving water body? Infiltration in areas with high de-icer application rates can result in exceedances of groundwater criteria. And this chloride-enriched groundwater may migrate into deeper systems or to local streams and cause exceedances. So that would be that last scenario that I talked about in the midway where we've got really high concentrations. That would be a good, well, I'll get into some recommendations here. It doesn't mean we can't infiltrate that area. What it means is we need to take some next steps and think about it a little bit. We need to improve our understanding and fate of chloride in groundwater. And that starts with I think the first recommendation that we've got in our white paper group is to try to develop a method for identifying areas that are vulnerable to chloride contamination. So that area in the midway, if there's no streams nearby, and if it's got a confining unit between it, the Prairie du Chien, and that, it's got really high chloride concentrations, but is that a problem? I think those are the questions we need to ask. If it's not, if there are no receptors nearby, maybe groundwater infiltration is a better choice compared to letting that water run off to a receiving water where it may in fact have a greater impact. And those are questions that I don't make the decisions for. Those people upstairs make those decisions. When we get these vulnerable areas identified, we want to monitor them. And as Sharon alluded to before, we're starting to get some better data for our deeper aquifers. We really need that data. They're going to be slower responding, but if we start to see those concentrations go up, it's almost like climate change. At what point, what's the tipping point? At what point can you not go back and stop a problem that's coming down the pike? We want to encourage infiltration in areas of low vulnerability, those places where we have fairly low concentrations of chloride. We want to get water into the ground through the infiltration systems in those areas. In areas that are vulnerable, if you're going to infiltrate, distribute your practices. Don't have one big system where you're pumping all the water down in. Put a rain garden here, a rain garden there, a rain garden there, and they're all going to, they'll interact, and you won't be putting that big one-time pulse and flush into the system. Properly site your infiltration practices. If you have a stream that's base flow fed and it's at risk, but your groundwater concentration is maybe 100 parts per million, so it's not exceeding the 230, put that rain garden or whatever, put it 6 months away travel time from your stream, so that by the time that water gets to the stream, it's going to damp out that wintertime. So it's a much more complicated way of siting the practice, but if we're in a vulnerable area, we probably should start thinking about these types of things. And use permeable pavements wherever we can. Now, permeable pavements can't be used everywhere. I-94 is probably never going to have permeable pavement on it. But parking lots, sidewalks, maybe some low-impact roads can take permeable pavement. So if we start promoting use of permeable pavements, they're not a panacea. They need a lot of maintenance. It's a fairly high maintenance intensive BMP, but if we really feel we're at risk in some areas for chloride, those might be areas where we want to promote this practice. Don't store snow in infiltration practices. Probably shouldn't do that anyways, but certainly don't do it because if you have high chloride concentrations in your snow. We have a lot of existing monitoring networks, and they've always sampled for chloride, but chloride's funny because unlike a lot of pollutants where you can kind of look at it 4 times a year, chloride, we've got that little window that I talked about where we need to rethink the way we're collecting data for chloride. And we're starting to see some of that. Larry Baker at the U is going out and collecting samples all this spring during the snowmelt. And that's what we got to do. We got to start collecting samples at the appropriate times and the appropriate ways. And we can use continuous recorders for specific conductors, for example. We can establish relationships for that with chloride, with conductivity probes. We can use that data to get some real-time information. And I believe that's being done in some places too. And there is research. What is the fate of chloride in infiltration soil media? And this gets at to your question here. We don't really know exactly why there's that lag in these systems. We have some ideas that need to be explored. We need to improve our understanding of chloride sinks and residence times in groundwater in particular. How long is the chloride going to be in the groundwater? If we move it in, is it going to flush out quickly, or is it going to stay there for a long time? And this is just kind of a sidebar. We need to continue research on chloride alternatives. This talk wasn't on management strategies. I noticed Brooke's not here. Maybe she's online, but decreasing the use of chloride de-icers is obviously the #1 thing, but there are plenty of other things we could do. Maybe we could use alternatives if they've been properly researched. You've seen more and more anti-icing happening. It's a much more effective way of applying de-icing material. We could establish chloride-free zones near receiving waters that are vulnerable. So if a lake is really vulnerable, set up a buffer around that lake where you don't apply road salt. Our technology is getting better. The first step should always be to go out and get the snow off the sidewalk or get it off the street. If you can do that, you don't need de-icer, or very little. Lower our winter speed limits, that'll go over well with the public. There's people out there that I swear want to drive faster than this. So, anyway. And then the one in red, of course, infiltrate in the right locations, especially with permeable pavements. And so ultimately, though, source reduction, at least right now, is what we have to do. Again, it gets back to the question of chloride versus surface water impacts. The chloride's going to have to go somewhere right now. And there's probably some situations where having it go to groundwater is not a good idea. We know that when it gets into these aquatic systems, it does mess up the ecosystem. That's data starting to show that. So, any questions?
Yes. So this is really good in determining kind of localized hot spots and problem areas. And I was wondering, this is kind of more of a management question. So has anybody taken like a little bit of a step back and did sort of a whole mass balance? Like I had my advisor did this to Michigan back in the 90s, and they looked at the gross loading of chloride from salting throughout the entire state and compared it to all the other fluxes for chloride. And it was such a small part of the gross chloride in that state that nobody really thought it would be, you know, a big deal long term, other than these localized scenarios where you've got focusing the things. That's a totally different setting, you know, structural basin, they have really high brines and everything too. But maybe on, like in the Twin Cities metro area, has anybody looked at just the gross amount of salt that's applied and, you know, kind of ins and outs over 100 years? Are we really going to have a bad problem with this so that we really need to start looking at alternatives, or can we just manage the hot spots and figure out where to infiltrate and how to infiltrate all the things that you discussed and manage it that way?
Eric Novotny, about 10 years ago, did a mass balance where he looked at chloride being applied from road salt and other sources too, but road salt was the main one. And they looked at the major river systems, what was coming in and what was going out of the Twin Cities, and determined, and I don't remember the exact number, but they determined something like 70% of the chloride on an annual basis is retained in the Smith metro area. So it's being retained. We know that. Long term, as we put more and more chloride into our system, does that number go down a little bit? Maybe. But also the study, and that gets at one of the research things that I point out. He didn't know where, they didn't explore where the sinks were. Is it groundwater? Is it lakes? Is it both? Is it soil? Where's the chloride getting held up? So the study didn't go that far. But it did show that most of the chloride that's being applied is being retained in the system.
Yeah, we know most of the source of this chloride comes from salts being used on most of our roadways, highways. Are we maybe meet with like MnDOT, counties or local government to come up with some alternative that are also still effective, but do not have much impact as chloride?
There's research being done on that right now. Brooke and working with Connie Fortin, they've done a great job working with the highway people to get them to implement good practices. And so MnDOT's getting pretty close to where I think where you about the best you can do with the chloride-based. There are concerns, and we hear the word acetate kicked around a lot, but acetate's got a biological oxygen demand issue with it. So there's research being done on some of these other potential alternatives to chloride-based de-icers, but right now I think we should exercise caution and just say, let's go out and start putting a lot of acetate on the roads or beet sugar or whatever, because we don't know. We may be creating another problem. But there is research being done on it, so that's.
Thank you.
Any other questions?
Any questions from WebEx? Feel free to send them in.
All right, I lied. It wasn't an hour. It was 57 minutes. Thank you.